Nice to have you here. I'm Tess. I'm a developer at Microsoft, and this is kind of not about my work. This is about a hobby I've had for about a year. Well, a hobby I've had for maybe 20 years, but more so last year, because a couple of years ago I started doing something called admin of code. How many people in here do admin of code? Okay, quite a few. So what happened was I was kind of doing admin of code and somehow kind of reinventing breadth first search, depth first search, all of these, not actually kind of like knowing the basics. And then I kind of got annoyed at myself because sometimes I couldn't solve a problem, and then I would go out on Reddit and find, for those of you who don't know what admin of code is, it's 25 days before Christmas. They put out like 2 puzzles per day, 2 really fun coding puzzles, and you can go back and look at it after and do them now if you haven't done before. But I got a little bit annoyed because I realized that like there was so much I didn't know, and so much I just had to copy code to solve. And I didn't want to do that, so I embarked on a journey to do leet code puzzles, 1 a day, every day for a year. And like a few weeks back, I was done, and now I'm not doing any of those anymore because it's kind of like a little bit like Pokemon, you gotta catch it. But it brought back the fun in coding again. Like some things that I was missing from when I went to college and so on. But it also brought back like a lot of knowledge that I could use in my day-to-day work at Microsoft. So I think algorithms have gotten a little bit of a, let's see, this is not triggering. Okay, 1 second. Okay. I think they've gotten a little bit of a bad rep as something that is only used sort of in interviews for big tech companies, and then never used in real life work. And although I do wish that my life looked like this is not a normal day at Microsoft, maybe at Google, but not at Microsoft. I do wish it was, but it does look like this. I'm doing a lot of other algorithm type things, and once I've started going through all these algorithms, I realized that there are so many places in my day-to-day work where I can apply these. So what we're going to do this session is we're going to go through the basics of a lot of algorithms. Graph algorithms, dynamic programming, things like that. Demystify them a little bit, and hopefully take it back to something you can use at work or for fun. So we're going to start off with one algorithm that I think most of you know, and if you don't, you will know it in 5 minutes. So I'm thinking about a number between 1 and 100, and your job is to figure out what that number is in as few questions as possible. And I'm going to always tell you if it's higher or lower. Okay? Yes, before I even ask the question, what would you guess? And you said 50. Why? Well, yes, binary search, but why? Why 50? Yeah, so we're basically, if we pick 50, then we've already discarded half of the search space, right? So we're discarding 50 of them. Pretty natural. This is what we've done since we were kids. And then you go through and you do this, I say higher or lower, and you pick another number. And then finally we get to a point where there's only one number left, and that is the number. Now, if you go through and you do this is called binary search, just like you said. If you go through and you do this for 100 numbers, in this case, we have 85 was our guess. If we would have guessed 1, and then 2, and then 3, and then 4, and so on, it would have taken us 85 times to guess the number. But since we're doing binary search, this is also called O of n, big O. But since we're doing binary search, it only took us 7 numbers, so 7 guesses. And it turns out that 7 guesses is the maximum that it will ever take to guess any number between 1 and 100. This is pretty powerful. The reason why this is happening is because log 2 of 100 is 6.64, because we're constantly divided by 2, and so on. Actually, if you don't know what log 2 is, it doesn't matter. Like, it's a number that lands, between 2 to the power of 6 is 64, 128, so 100, that's in between, so there's going to be 6 point something. And since we can't do 6 point something guesses, we're going to do 7 guesses. But if we look at this, and we think about it, actually, let me go back once. So what if it took 7 guesses versus 85? We got computers, they're super fast, it doesn't really matter. But if we had 1 million numbers, then we would have looked at the number, we would have looked at a maximum of 20 guesses versus 1 million. Now that's starting to rack up. Still not a big problem for a computer to guess 1 million, but if we had 1 trillion, we would be comparing 1 trillion versus 29. So you can see that something like binary search is makes it much more efficient than a literal or like a search. What do you call it? Like when you go like 1, 2, 3, and so on. So we can use this in any scenario where we have something that is sorted, where we can say lower or higher. So looking at a sorted list, we can determine, for example, what index is number 7. We start in the middle, it's lower, so we now narrow our band to the lower space, and then we take the middle of this, which is 3, it's higher, so now we've narrowed it down to these 2, and so on. So even in the sorted list, this is a very useful algorithm to use. But it gets even more interesting. So this is kind of where people stop with binary search. This is what people generally know. But then there's a whole other set of algorithms that we can use binary search for, or another set of problems. We're going to look at a problem called Coco eating bananas. Now I'm going to use leet code problems, but you can kind of imagine them being real life problems later. So what this is we have Coco, who's a monkey, and she gets paid in bananas, in piles. So she might get a number of piles, one pile with 3, 6, 7, and 11 bananas. And then her handlers tell her, you need to eat all your bananas in 8 hours, because we're going to come back in 8 hours, and we're going to take whatever is left. And she has a quirk that she wants to eat as slowly as possible, but she also wants to eat as many bananas as possible. So she wants to get done in 8 hours, but she wants to savor her bananas. So now we go through, and there's one more quirk. She can only eat out of 1 pile every time, or every hour. So if we would take 1 banana per hour, we would end up in 27 hours, way beyond the 8 hours. 2 bananas per hour. Now we can see it's not like 1.5 hours here, because you have to have, you can only eat from 1 pile at a time, so it will be full numbers. So this takes 15 hours. 3 bananas per hour take 10 hours, and this takes 8 hours. So finally we reach, by linear search, we find out that our lowest speed is, that we can actually do it in 8 hours, is 4 bananas per hour. So that's fine, until you realize this, that the constraints of this problem is that we can have 10,000 piles and 1 billion bananas per pile. Now, that's a little bit bananas. Maybe we're not talking about Coco, who's a monkey, and bananas. Maybe we're talking about, I don't know, like things I'm working on right now. Azure Batch. Trying to do like as many tasks as possible in a certain amount of time. So the problem is just changed shape. So what do we do now? Because we look at this, and we do this linear search, we realize that we need to search all the way from 1 to the maximum number of bananas that exist in any pile, because it could potentially be this number. So this lands us at the number of bananas that can exist in a pile times the number of pile. This is how many computations we're making to solve this problem. Potentially, like this is the max number that we're making. And in this case, that would be, I don't even know what that number is, 10 gazillion calculations. That is a lot. In fact, like, I think that we don't, like our computers couldn't even handle this, the type of computers we normally have right now. But what if we do this instead? What if we use binary search? So we say, I'll take somewhere between 1 and a billion, which is like 500 million. And I'll say, did I make it? And if I didn't make it in time, then I have to lower my speed. And if I did make it in time, I can go higher. So that's the same question as what number are you guessing? And it looks like this in code. You don't have to remember this code, but just know that this code is not like super hard. There is like even a template for binary search. You just need to figure out this piece, which is what we're going to kind of compare. But otherwise, it's just the same binary search that shows us and guesses what number we're guessing. And now the result is not 10 gazillion, but 10,000 times 29. So that's 290,000 calculations instead of like the super big number. Now we're talking a real use case for binary search. I've shown a few times big O of something in this case, and I'm sure most of you probably have heard of big O notation. Big O notation is a way to compare different algorithms. So it's a very rough calculation. It's not at all something that can actually compare them, but it's a way to kind of like discard some and include some. And just because I'm going to use this a little bit, I just want to show like super quick for those of you who are not familiar with Big O, what we do. First off, Big O tells us the worst case scenario for doing any type of code. So we're looking at a list of fruits. And if we want to go through and just sort of like print out all the fruits, this will take us n times, a maximum of n times. So, and this will be O of n. If we do it in a double loop or a nested loop, it will be O of n squared, because now we're looping to, if we have 100 items, we're going to do 100 times 100 loops. If we just print out something unrelated to the size, this is like independent of the size, this will be O of 1, or O of a constant. And we don't care if it's 1, or 5, or 20. It's not going to be O of 20, it's just going to be O of 1, because it's like O of a constant. So, because we're doing rough calculations, we're removing the constants here. We saw with binary search that we have O log of n. So now the question kind of comes up, will we win something by first sorting and then doing binary search versus doing linear search? Thoughts? Well, the answer is no, because the quickest sort that we can do is actually n log n. So quick sort or merge sort, which is the sorts we normally do in link or in anything, or n log n. So you don't get any benefits from first sorting and then doing a binary search. That's more expensive. If you want to look at sort of like how important it is to do O of n versus O of n squared, this is a little bit like how these trajectories work. And if you've got an algorithm that's roughly linear, that's usually a pretty good algorithm. Now I did say that you cannot have a faster algorithm than O of n, or O of n log n, but here is an algorithm, a sort algorithm that is actually O of n. So what this does is you take a set of numbers, and then for each number, you let it sleep for whatever number of seconds that that the number is, and then we'll print them out in order. This technically looks like an O of n, because we're only doing one loop. But is this more efficient than merge sort? Obviously not. I'm bringing this up a little bit like a fun thing, but also because I want to show you that you shouldn't think blindly O of n is better than O of n log n, for example. It depends, like everything. Okay, so going back to this again, there's one thing, and this is something that's very useful generally in our programming, and that's if I want to take something out of a list. This is something how many here are C# developers? Yeah? So you probably use link all the time and do link selects and things like that. Link selects are nice, but they're usually linear search. So if you ask if peach is in this list of fruits, it's going to maximum have to go through all the items. However, if you want to speed it up and you have numbers that are distinct, so there are no duplicates and there's no importance of the order of the list, you should instead use a hash set or a dictionary. Because suddenly if we change it to a dictionary or a hash set, the curly brackets will change this. This is Python, but it doesn't really matter. Then it becomes a constant lookup. Because looking up something in a dictionary or in a set is constant. And this is quite important if you have a big set. Like if you have something like 1 million items, and you want to keep looking up things by keys, it's definitely worth the while moving to a dictionary or a set instead. So, enough of that. Let's move into some more algorithms. Or actually, before we move into an algorithm, I want to move into a data structure that's quite useful and quite often used in many algorithms that we have. So we're talking about graphs. So a graph can be something like a Facebook set of friends. These are people who are connected to each other, and we call this as a non-directed graph, because I'm friends with you, you're friends with me, there's no direction in this relationship, it's always always have two directions. However, if we look at something like Twitter, where you have followers, and they might not necessarily follow you back, that's called a directed graph. And it kind of has a little bit of importance when you look at the algorithms for it. We can also have a graph like this, where we have the nodes are cities, and then the edges are rows. So we call nodes, edges, sometimes these are called vertices too. But in this case, the difference is that these nodes these edges have weights. So not all of them are created equal. It takes longer to go from Stockholm to Oslo than it does to go from Stockholm to Västerås, for example. So that's called a weighted graph. Here it's another weighted graph, but this is also called a disjoint set. So some problems that you'll encounter will ask you, for example, how many different groups do you find? How many different groups of friends do you find in Facebook? Or how many different set of tasks? These kind of things. And how big are these groups? What's the size of the biggest group, for example? These might be some common problems with graphs. Sometimes the graph doesn't look like a graph. It looks like this. So this is also a typical graph where every place you can be on in this maze is a node, and all the other edges that you can, or all the other nodes that you can reach from this node are your neighbors. So in this case, the edges is these like stepping from one node to the next. It might look also something like this. You have a horse on a chessboard. Same thing, all the squares are nodes, but now the neighbors are these instead of like the ones that you had in the mix. And in this case, you don't actually draw out the graph like this. You would dynamically generate these next nodes. There are some special graphs. Trees, for example, are directed graphs, but they have special cases where they might only have so many children or so. We have binary search trees, very useful for when you want to do searches in big amounts of data, because here with 8 at the top, if I say does 6 exist in this, I know that 6 is definitely going to be on the left side of 8 because it's less than 8. And therefore, I've now kind of discarded the whole rest of the tree. So it's super useful to search in large amounts of data. We have this one, that's a trie, or a prefix tree. And this one is used, for example, when you're doing paths. So if you think about, for example, in ASP.NET, you type in maybe, or actually in an API in general, type get /jobs / some job ID, and you want to know if that's a valid path or not. Then the server doesn't actually go through and look at all of these strings that you put in and see if they're valid or not. It probably uses prefix tree to figure out what it is. Or even if you're doing, text completion on your phone or something. So the way this works is like this. You have all the possible answers in your tree. These are all the possible words in this dictionary. App, ape, apple, ball, banana. These are the different words that can exist in this. So when you start typing, you're from the root, you type A, you know that you're now sort of like these are the only possible words that you can have. If you try C, you know that you're already out of your dictionary, so you don't have to worry about anything else. But I start typing A, and then I type P, still in the dictionary. I try P, and suddenly I reach the end, and it says, okay, so this is a valid word. This is a good word because this is an end node. And from here, if I try L, I'm still in the dictionary. E, I found the word. So this is like a very quick way to go through and do text completion or path completion or things like that. A trie or prefix tree. And then we have linked lists, for example, but that's used a very specific version of a tree with only one child. So if we look at this graph, because it's easy to draw graphs, but how do you actually implement them on a computer? So what we can do is we can either implement them as edge lists. So this is describing all the edges that exist in this. There's an edge from Oslo to Stockholm, Oslo to Copenhagen, and so on. This is a very efficient way of describing a graph, but it's also a very inefficient way to describe it when you're going to do an algorithm on graphs. However, it's useful also when you have weights, because we can just add on the weight at the end and we're good. But a more efficient way to describe this, if we want to do algorithms on it, is actually doing an adjacency list, or an adjacency graph. In this case, we then have Oslo, who has 2 neighbors, Stockholm and Copenhagen, and so on, because now we know that whatever node we're on, we can quickly get to all the other nodes that we can get to from there. And if we want to add on, for example, a weight, we can represent it as a dictionary. So let's get into some algorithms. So there's really 2 algorithms to learn for graphs, or 2 big algorithms to learn for graphs. One is DFS, depth first search, and one is breadth first search. And then there are many variants of this, Dijkstra or A-star or things like that. But I just want to go through these two because they're quite, at least in my mind, easy to kind of understand the concept of. You start off, in this case, at the man, and you want to get to the star. So what we do is we say, what nodes can I get to? And I add these to a list at the end of the list. And then when I get there, I might have multiple nodes that I could get to, multiple children. And then I take the last one from the node, like the last children, the last child, and I go to its child or its neighbor, and 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 its neighbor, like this, until they either reach the end, or I reach a dead end, in which case I go back to the last time I had a choice, which is now going to be the end of the list. So it's not many lines of code to implement this. There is, however, a problem with this, because we did find a path, but we did not find the fastest path. Right? We can all see that it completely missed this one. It would have been sort of what we ideally would look for, maybe in a lot of questions. We want to have like the shortest path, the shortest number of steps, etc. So this is great for exploration, but not great for finding shortest path. But there is an easy fix to this. We take this, which is a stack or a list, and we change it to a queue. A queue has different state. We take the next item, we take it from the front of the queue. So it's, instead of last in, first out, it's first in, first out. And by doing this, what happens is this. We go to the neighbor, now we go to all of its neighbors, and all of its neighbors, and all of its neighbors, and this will automatically get us the shortest path instead. Just with a simple change from stack to queue. Now in Python, this is written in, that's a double-edged queue, a deck, but there are, of course, similar techniques for C#, etc. One thing we do also do is we add in this visited set. So the visited set is so that we won't end up kind of like in a loop where we constantly go around, hitting the same 4 blocks all the time. So this is normal, like we have graphs, we have these mazes, very common reasons why you would use these algorithms. But we're going to look at a completely different kind of problem where we can also use this. So you might recognize this. It's a jug problem from Die Hard. Anyone know what this is? Maybe? Well, I'll explain it for those of you who don't. So what they had was they had 2 bottles of water, one that could take 5 gallons and one that could take 3 gallons or liters or whatever. And they wanted to end up with 4 liters of water. And you can only fill them like either full or like pass from one bottle to the next. I'm sure you've all at some point in your life played this game. So this is our original state. We fill up the 5-liter bottle. Then we pour it over into the 3-liter bottle. Now we have 2 liters in the first one. Then we fill up, we pour them over into the small one. We fill up the 5 one again, pour it over, and suddenly we end up in the state where we have 4 liters in the big one, and we're done. What does this have to do with graphs? Any guesses? Okay. All of these can be represented as states. Like states where we mark them sort of like by how many, 5, 2, 5, and 2. And we know that there is a transition between one state and other states. So we definitely know what possible states we could get to from 5.0, for example. We can either pour it over to do a 2-3, we can pour it out to get to 0, 0, or we can pour in like the third one, or like the small one to get to 5, 3. These are the only states we could get to, and we can calculate this. So we can then turn it into a graph like this, where we have all the nodes and we can calculate all the states. And suddenly our job is to go from 0, 0 to any state that contains 4. And this is a very, very typical reason why you would use one of these breadth first search or shortest path search. So, in advent code or in real life, actually, both of these are very, very useful techniques. Now, we can use breadth first search if we want to do the shortest path like this. If we add on a different kind of issue to the problem where we want to add in that you also have to get a key to get through the maze, the only thing we change is that each node in our visited list is not only the location, so it's not only this node, but this node and whether or not you have the key. So it would be like the top node would be 0, 0, 1, or 0, 0, 0, depending on if you have a key or not. And that's essentially the only change you have to make, and then you have the same old graph problem again, and you want to reach to the end with it. If you have something with weights, you do have to resort to some other algorithms like Dijkstra, A-star, or even Bellman-Ford. Bellman-Ford is if you have negative weights. Because the shortest path, like the fewest number of steps, might not automatically equate the shortest route. Like if I go from here to, I don't know, to Stockholm City, to Västerås, that might take 2 steps, but that's still a shorter route than if I do a direct way from here to Oslo, for example. So that's why you have to use these other algorithms. I don't have time to go through them in detail, but they're not actually all that complicated to understand in a few minutes. What I do want to go through instead is I want to show another type of problem that is also a graph. And this is one that I find is very useful for mail work. So in this case, we have a number of courses, school courses. They have prerequisites. So in order to take course 1, you have to have taken course 0. In order to take course 2, you also have to take course 0. And in order to take course 3, you have to take course 1 and course 2. And now our job is to figure out which order should we take these courses in order to preserve this prerequisite demand. And this is called topological sort. So we sort them from the root to the end. We can see in this case that just from visual inspection, it would be you take 0 and then 1 or 2 and then 3, or you can take 0 and then 2, 1 and 3. So both of these are very valid options for this. None is better than the other unless you put other restrictions on them. How can we calculate this with an algorithm? The way to do this is by doing this. We take the one that doesn't have anything depending on it, 3. We save it away and remove every link to that. So anything that is a prerequisite, or that has is a prerequisite. And now we have 1 and 2. So we can take either of them and do the same thing. Take the other one that doesn't have any prerequisites anymore. And finally that one, and now we just turn it around. And this is how easy it is to do a topological sort of a graph. And this is a very typical problem, and at least very often in advent code you get asked to sort something in order. Another technique that we use, except for graph problems, is something called dynamic programming. And this has been something that's kind of been a little bit highbrow, like people kind of like to say, oh, I'm using dynamic programming, I'm so smart. Well, it turns out dynamic programming is caching. And who here has not ever cached anything? If you have, you use dynamic programming, so you can be in the cool club. But I'm going to show you, though, it's a little bit of special type of caching still. So if we look at the problem, I'm sure you're all familiar with Fibonacci. If you're not, basically to find Fibonacci 3, you take Fibonacci 2 plus Fibonacci 1. This is the standard first thing you'll try is to learn recursion in college. If we look at Fibonacci, for example, if you try to calculate Fibonacci 50, just for this base recursion, you'll quickly find out that your computer will not be able to hardly handle Fibonacci 50 because they're going to have to do a lot of work to figure that out. And the reason is this. Like if we look at Fibonacci 5, we need to figure out Fibonacci 4, Fibonacci 3, and they quickly expand to be very, the tree gets very large. If you picture this tree now with 50, that's a large tree. But we can see in here that there's a lot of things that we're doing over and over again. Like we're calculating Fib2 3 times in this very small example. So what if we didn't calculate it, but we cached it instead? So we didn't have to go through all the things underneath it. So instead of writing this code, we would write code like this. We have a cache for all of them. If we don't find it in the cache, then by all means calculate it. But if it's in the cache, you just use it. Like this. And in fact, in something like Python, you can just add the add cache. And this automatically dynamic programs your code, And we're saving a lot of computations with this. So this is something I use quite a bit at work because instead of redoing, for example, database queries or things like that take a lot of time, and if there are overlapping subproblems, this is a very effective technique of reducing that. Now, of course, everything comes at a cost. If we go back to look at this, the cost of this is that we have to save the results, right? So we trade efficiency for memory in this case. The other thing that we also need to remember is that n in this case has to be a hashable item. So it has to be an integer or a string or something like that. Something that could be a key for a dictionary, because it is going to be a dictionary in the end. So it could be a list, or it could be, something that's not hashable. So you have to turn your function into something that's hashable, or your parameters into something that's hashable. We can also do this the other way around, and the other way around being that we start not at the end, but at the beginning. So in order to figure out fib of 50, we start with 0 and 1, and we build until we get to 50. So what we win by this is that we're now not doing a recursion, which in itself is a little bit expensive. But what we lose by this is sometimes your problem doesn't have to go through all of the different steps from 0 to your number, and you lose that part of it by using tabulation versus normalization. So using whichever one of them depends a little bit on your problem set, and if you have like, if you know you're going to calculate all the numbers from the start to where you're going, or if you're just going to need a few of them. So this is great for Fibonacci, but how can we use this in a real problem? And I say real, but I mean, there's still plug-in code problems. So in this case, what we have is we have a robber, and the robber is going to go through and rob houses. This is how much money there is in the house. Not very much, it turns out. But he's liking his job. One thing though is that he cannot rob 2 houses in a row, because if he does, he'll get caught, obviously. So he can, for example, rob this house, but then he couldn't rob this, he can only rob these people. You understand the problem? One way of solving this problem and figuring out like what the maximum loot he could possibly get is by doing this. We count out like all the possible combinations that we do. We remove the ones where we have houses that are next to each other. And this sounds like I'm using binary numbers. It must be very efficient. I think it's perfect. The only problem though is that if we have 100 houses, this is how many calculations we'll do. 1.27 times 10 to the power of 32. That, my friend, is a lot of numbers. This is me waiting for that to finish. I'm not looking like that now, I think. And this is me remembering that I do know dynamic programming, so yeah, we're not gonna wait. So what can we do instead? What we can do is this. We can turn this into a little bit of a different problem. So we say, if I'm starting here at house 0, I have a couple of options. I can either A, rob this house, in which case I can now not rob until, I can now only rob from house 2 and on, or I can not rob this house, and now I can rob from this house and on, right? If we turn this into code, it would look like this. The maximum loot I can get is 0, is robbing this, and then the max loot I get from 2 and on, or skipping this, and then I would get the max loot from 1 and on, right? Now, does this look very much like Fibonacci? I think it does, right? So now we can turn this into the same thing, like write some code, add cache on top, and we solve this problem. And it turns out that instead of 1.27 times 10 to the power of 32, we are looking at 100 calculations for 100 houses. This is a lot of speed up, I think. So is caching and dynamic programming and these thinking about it like in these recursive terms is very, very useful. Now, we have dynamic programming, but we have a special case of dynamic programming that's called a sliding window. So sliding window goes something like this. We have an array, and we want to, we want to summarize, or we want to find the largest subarray of size 4. So by largest, I mean the sum should be largest. So we want to know which sort of like window of 4 has the largest sum. We'll calculate this. It's 2. We'll slide over a little bit. It's 51. So on and so forth. So this is like the brute force version of this. It's quite simple. But if you look at the yellow colors here, you'll see that we have a lot of overlapping subproblems. In fact, the color kind of tells you that -6 here is calculated not only once, but it's in 4 of the calculations. So this is a problem because just like with Fibonacci, we don't want to kind of keep redoing the same calculations over and over and over again. So what can we do to solve this problem? What can we do to avoid sort of doing this sum? One way we can do is that if we start off with this, which we know is 2, when we move to the next one, we're not actually going to sum all the numbers, but we're going to take our previous sum that we already had, remove the number that we are no longer using, and add the number that's new to us, right? And then we'll go through like this. Do that. Now you might say, okay, so you lost 1 calculation. What did you actually win from this? Well, what if the k was not 4, but the k was 50? Now we've gone from summing up 50 numbers in every window to summing up only taking the last sum minus what we lost plus what we added. So I've gone from 50 to 3. When you use sliding windows like this, you're always going to be running it O1N. So sliding windows are very useful. Let's take an application of this. So we have this guy who's a grumpy bookstore owner, we call him Bob. Sometimes he's happy and sometimes he's sad. And every minute there's a different number of people coming into his store. Depending on whether he's happy or sad, they will buy stuff or they will not buy stuff. Very influential, his mood is. So the problem now is that he has an opportunity to do something, eat a pill, for example, that makes him happy for 3 minutes. But he doesn't know how to optimize this. When should he take this pill in order to kind of like maximize his happiness? We're not judging. I'm just saying, like, this is a fictive problem, we're not judging. So, how do we solve this problem? We can do this. We can say, when he's happy, it doesn't matter if he's taking the pill or not. He'll always be happy. We can kind of discard these, this sums up to 10 people that will always buy whether or not he takes the pill. We'll call them zeros. And now it becomes a max sum problem, right? It becomes a window of 3 where we can maximize the sum. And we do the exact thing that we did just a moment ago in the previous slide. So this is a typical problem of using a sliding window. Like similar, maybe a more real world problem here would be you have a rebate in Azure, but you only have like an hour to use it, and you want to know exactly which hour should I use it to maximize my properties, for example. So that's one way to do a fixed sized window. Now we're going to go and look at a slightly different window, which is a shrinking and growing window. So this is Anne. She likes fruit, but she only likes to have 2 pieces or 2 types of fruit in her basket at the same time. If she goes 3, that's, not good. And she's going to pick fruit from every tree, and we want to know how can we maximize the amount of fruits that she has in her basket. So in this case, we'll use a slightly different technique. We don't know what size our window is, but we'll start out with a window. We pick up the apple. We grow it a little bit. Pick up the orange. Still good. Still good. Still good. Now we have 3, so we're not good anymore. So now we shrink it all the way until we still have only 2 types of fruits. And then we grow it. We're back again. So we shrink it. And whatever maximum size this window was, that's our maximum range. So this is the technique you would use if you don't have a fixed rate, but if you want to maximize, for example, a sum in an array that might have positive and negative numbers, for example. So those were a lot of algorithms, and I hope that somehow all of these algorithms have given you at least something to think about. You can take that either to solve a bunch of advent of code problems or in your real work, hopefully in your real work too, because that's a little bit what we do. But if you get interested in algorithms and you want to do a lot more with this, here are some tips for some sites that you can exercise this energy you have for solving problems. So leet code I've talked about before. So leet code has this daily leet code puzzle that shows up here. It's free. You get like medium, easy, or hard problems. And if you're feeling good about yourself, you can also, on a weekly basis, go in and compete. And the competitions are completely sort of, no one will ever know that you're competing or what your number is. It's only for yourself, essentially, but you get ranked with others. And I find it to be a very nice thing to do on the weekend. What it is like 1.5 hours where you get fed 4 different problems, and you have to solve them as soon as possible or as fast as possible, and then you get penalized if you don't if you submit an answer that doesn't pass all test criteria. But this is a fun thing. There are many, many other sites like this, CodeChef, lots of others, but I really like LeetCode. And then for those of you who haven't tried it, add in the code. There's, I think 2015 was the first year, so if you've never done this, you have a lot of stars to pick up. And I envy you because I wish I had. And then finally one, if you're more math inclined, Project Euler might be one that you might like. But I hope you go out there and do a lot of algorithms. If you are interested in algorithms, I am always interested in talking about them on Twitter, for example. I'm Tess Ferrandez on Twitter. If you want to talk to me there about algorithms or, I don't know, Azure or other things too, but preferably algorithms. Thank you so much.